Welcome everyone to the first session of in Track 2 at USENIX Annual Technical Conference. This session is chaired by Marcelo Martins and Dilma de Silva. I'm Ketan Bhardwaj, Georgia Tech, and would give you a sneak preview of what's to come. So first thing that sort of caught my eye was the title of the session, like dogs never get tired. So I thought, let's just tell a story about the dogs. Today, we have a lot of cloud providers which are powering a lot of our applications. But then we all know there are limitations of the clouds in terms of the amount of data that needs to get into the cloud for it to processing that was sufficient for most of the use cases that were there in the past, but newer use cases like augmented reality, huge video surveillance processing, and autonomous cars and things like that are pushing the boundaries of what needs to be in the infrastructure. So, and it's not that something new, but a lot of stakeholders already knew it, and there were developments in form of CDNs from Netflix, Google. What they ended up doing was they were primarily used to reduce backhaul demands and take latencies of accessing those web services from tens of milliseconds to few hundred milliseconds, and they range in the order of like thousands of global locations, and that was cool. But then what happened? How fast actually we need the network to be. So Pablo Rodriguez from Telefonica shared this picture in one of the conferences, and this just shows you how important lower latency and the backhaul bandwidth is. So that sort of led to emergence of what we now refer to as edge computing, and what this session is about. There are a lot of companies who are offering edge today, be it AT&T, AT&T with Microsoft, Verizon with AWS, DT is also doing something, and more recently Cox opened up their own edge infrastructure. But the question that is still a question is, where are all these edge located? Where actually is the edge? So this edge, it ranges from central office locations to base stations to your homes and offices and enterprises, and finally, actually, the edge could also be in the devices themselves. And that brings us to this particular session. On a very high level, to put the context of the work that will be presented in this session are, how is edge useful, and what system support, infrastructure, and help does edge need to deliver on reduced latency and savings on the backhaul bandwidth, primarily focusing on the power and energy constraints at edge, and also what are the systems and mechanisms that can be explored to handle multiple applications at the edge. So let's go over each of the papers. The first paper in the session is prediction based on power oversubscription in cloud platforms. Well, there's no hiding the fact that power is important, right? And even in the public clouds, power oversubscription is limited. That simply because you don't know what workloads are running. So most of the current work in oversubscription related to power relies on hard to get info. So they don't consider applications, for example, virtual machines and containers as black boxes, instead get some application hints, and that sort of makes them limited. And not just limited in terms of what they can do, but also they tend to be reactive and require expensive mechanisms like VM migrations and things like that, which are not suitable, especially for edge computing scenarios. So what we will hear from authors is their prediction-based approach and how they predict VM criticality and utilization, and by accurately predicting those things using ML models and algorithms, what they end up doing is they are able to protect some of the critical VMs of incurring any performance overheads, and also do that through intelligent placement and changes in Azure's VM scheduler. And the results are promising. They show twice as much oversubscription possibility that is achievable today. And in a similar vein, the next paper, which is related to energy and power, but in a different context, it's basically on video streaming. Now, there's no question that video streaming on mobile devices is a big use case, right? It potentially can be called a killer use case for edge. Now, what happens with power and energy is it remains in cumulative nature, right? And because of that, even the most widely used application adaptation or offloading, if I may say that, that is known as adaptive bitrate, ends up creating these oscillations, and makes it difficult to actually tie in quality of experience of users to the application adaptation that happens. And perhaps more importantly, it's just difficult to predict energy usage. And to address those challenges, the authors will be presenting a integrated proactive ABR adaptation for Video 360. In this paper, they've done a really good job at comparing the differences and trade-offs between reactive and a proactive approach. And instead of relying on like a black box approach to power and energy, they have sort of divided it into function-wise. They've allocated power to different functions of the video streaming application, which is rendering and decoding, and they provide a practical control algorithms and show how that can benefit not only in the cloud or mobile devices, but also more and more at edge, where all of this video processing is going to happen. Now, going in the same sort of scheme about cameras, the next paper sort of claims, next paper that you're going to hear about is, we know there are a lot of cameras, there's a lot of video processing, and a lot of it is surveillance, but authors sort of perhaps correctly identified that the huge amounts of videos that these cameras are producing are cold. There's nothing interesting about it, and especially for the cameras in surveillance, which sort of handle ad hoc queries. Ad hoc queries are queries which are very static in nature. You know what you're looking for, how often are you looking for these things, and things like that. So they make an important point. Why stream at all? Like, even to edge, if you're going to stream it, it leads to a lot of spectrum usage, and they sort of argue that cloud processing is only needed if more accuracy is needed. So in that sense, they're presenting a zero streaming approach, which leverages the spatial skew in landmarks, because most of the stuff in these videos is static and you can identify them, and they're leveraging cloud to provide increasingly complex and more accurate operators on them. It's a interesting multi-pass, multi-operator mechanisms that they outline in their paper, which leads to 100x more video in real time. And if you're interested in anything related to video, you should hear them. And the final paper in the session is slightly different than edge cloud processing. It's for mobile application switch, but to put that in perspective, this is the kind of challenge that you would also face in the edge computing settings, where it needs to support multiple applications. So today, every one of us uses more than one app, and then switching between them can be faster. The cause identified by the authors was the demand paging that happens in the underlying system is slow and requires careful low-level design. The authors show that it is possible to predict likely to be accessed pages and pre-page them, which ends up creating faster app switching times, but at a cost of additional CPU and disk bandwidth usage. That's all for now, and for no particular reason, here's the picture of 3 dogs that we used throughout this presentation. Enjoy the session.
Hello everyone, welcome to the preview of operating systems and hardware session. My name is Sudarsun Kannan. I'm an assistant professor at Rutgers University. Along with Michio Honda at University of Edinburgh, we will preview 4 operating system papers. I'll start off with 2 papers on memory management. As we all know, scaling memory capacity for applications without increasing management cost is becoming extremely critical, but also tedious. Similarly, scaling memory protection and isolation for large-scale address spaces is also becoming equally critical. The first paper that we are going to talk is about beyond malloc efficiency to fleet efficiency, a huge page aware memory allocator. The authors argue that there are several types of allocators which are designed for specific application needs. For example, increasing concurrency or reducing fragmentation, minimizing L1 misses, increasing locality. Unfortunately, most of these allocators are not optimized for huge pages. To recollect, huge pages are capabilities in the operating system that allow applications to allocate larger than 4K pages and reduce page allocation cost as well as increase TLB coverage. However, current allocators in combination with huge pages could increase fragmentation and are inefficient for warehouse scale systems running several applications. To overcome this, the authors proposed Temerai, which is a huge page aware user level allocator by extending tcmalloc. Temerai aims to densely pack huge pages grouped into few saturated bins. Further, it balances memory usage and page allocation costs through adaptive huge page release. Intuitively, Temerai divides allocators caches and serves requests from different caches. For example, small requests could go to a huge filler cache, medium requests could go to a huge region, and large requests could go to a huge cache. The paper proposes several optimizations to reduce allocation overheads and increase usage of huge pages. But on an average, it reduces TLB misses by up to 6% and overall memory reduction by up to 26% on a large fleet of applications. Similar to memory capacity scaling, scaling memory protection in a hardware-based enclave system is also becoming challenging. To give a brief overview of hardware enclaves, these are hardware abstractions that support trusted execution on untrusted platforms. More specifically, hardware enclaves provide secure boot, on-chip program isolation, protected external memory, execution integrity, and other capabilities. However, hardware enclaves, for example, say SGX, are not without challenges. First, they have the memory partitioning and isolation is not scalable, which means the current hardware only supports up to 256 megabytes of enclaves in some architectures, whereas in others, they restrict the number of enclaves. Similarly, they require static partitioning even before an application is run. Hardware enclaves also provide memory integrity protection by storing hash of the memory pages, but this also incurs huge memory overhead in storing the integrity information. Further, hardware enclaves today also require high memory initialization time. Now, this could be impractical for several serverless applications that must immediately boot and run. To overcome these challenges, this paper Penglai proposes a scalable secure memory protection mechanism for enclave. At a high level, it introduces a new abstraction called guarded page table, where the secure application pages and unsecure pages are mapped to separate host page tables and enclave page tables. As a consequence, an unsecure host app trying to access a secure page via a secure page table will get a memory protection fault, and as a consequence, memory protection is delegated to the hardware. Further, to scale integrity protection, Penglai introduces mountable Merkle tree, which provides a capability to design a subtree structure and store only the subtree structure either on drive or in memory. As a consequence, reduce the memory storage overheads. Several other details about this is discussed in the paper. I'll now hand on the baton to Michio. Thank you.
In this part, I cover background and context of the other papers in this session, NROS and NanoPU. In the past, computer systems had a single CPU core and the software was single-threaded. This means that concurrency control was relatively simple. I/O devices like disks and networks were relatively slow as well. Then, systems started to have multiple CPU cores. Operating systems initially relied on a giant lock, which allows only one thread to be active in the kernel. This design was used to keep most of the existing single-threaded kernel code to work, but of course it is inefficient. Many OSs then started to use fine-grained locking to increase concurrency, and reader-writer locks and their variants such as read-copy update or RCU locks. Not surprisingly, these locks significantly increased the complexity of the kernel code. Even worse, NUMA systems emerged, where multiple CPU sockets or packages are installed with their own memory slots. Memory access to a remote socket or NUMA node is slower than local memory access, so operating system kernels started to support NUMA locality-aware memory allocator or thread scheduler. Operating systems became even more complicated by fast I/O devices, such as NICs and SSDs, because saturating such fast I/O devices need new techniques and APIs. Such techniques and APIs are designed to handle frequent hardware interrupt, load balance between multiple CPU cores, and reduce system call or context switch overheads. All of these new hardware features made kernel code complex and error-prone. Let's take a look at an example of kernel code. It locks a TCP socket in a non-sleepable way because it is currently running in the interrupt context. Then it checks another socket lock to see if it has been locked by a system call context or not. It also must take care of the reference count, which is another concurrency control primitive. Unfortunately, despite of such complexity, OS kernels are still not scalable to many CPU cores or fast I/O devices. This is a common problem space that the two papers I'm introducing next try to solve. NROS, probably stands for Node Replication OS, solves this problem by a new OS design. Let's take a look at the diagram. Unlike traditional monolithic kernels like Linux and FreeBSD, NROS creates a kernel replica on each of the NUMA nodes and synchronizes these replicas using a shared operation logs, which are in the middle of the picture. This design simplifies the kernel programming, such as implementing a file system. It also utilizes shared CPU caches within the NUMA node efficiently. This design might not look really scalable, but the authors invented many interesting techniques, such as batching synchronizations, timely event notification to process logs, and read concurrency. It is also quite useful to have a NetBSD-based library OS to run regular POSIX applications. So don't miss the talk by the authors. The other paper is about NanoPU, which co-designs NIC and CPU. Traditionally, a NIC places receiving a packet in the main memory, which is called direct memory access, or DMA. Since access to the main memory is relatively slow, modern NICs instead place receiving packet in the last level CPU cache, which is called data direct I/O or direct cache access. NanoPU moves this technique one step further. The NanoPU NIC places receiving a packet in the CPU register, where the application can access the data with a single CPU cycle. This single cycle data access is also very useful to reduce tail latency. Tail latency is very important in the data center because a single request processing usually involves multiple network RPCs, such as getting the small value corresponding to a key. This means that delay of any of these RPCs delays the entire request response time. This is why tail latency is important in data centers. It is also great that NanoPU does not only cut the host network stack latency, but also queues in the network by implementing state-of-the-art transport protocol, NDP, in the hardware. I am sure that the authors will present a very exciting talk. Thank you for watching. I hope you understood the context of the operating systems and hardware session. Enjoy the session at 7 a.m. on Thursday.